Hello everyone, and welcome to today's Focus On webinar from GenQA, which is focusing on PGT-M, so the pre-implantation genetic testing for monogenic disorders, and really to start giving you an idea of some of the journey that we've come on as the external quality assessment provider for PGT-M over the last 12 years. So I'm Professor Sandy Deans, I'm Director of GenQA, and I'm joined today by my colleague Farah. Farah, do you want to introduce yourself?
Hi, I'm Farah Khwaja, one of the Deputy Directors at GenQA.
And together we're going to give you a summary of the work that EQA has been doing, the scheme provider in the field of PGT-M. And also we're really pleased and delighted to be joined by a range of key experts in the field of pre-implantation genetic testing and authors of a recent recommendations publication that came out that we're going to talk you through today. So I'm very pleased to introduce the authors, and I'll start with Anil. Do you want to say hello, please?
Hello, my name is Anil Biricik. I am the Chief Scientific Officer of Aerofen's Genome laboratories in Italy.
Thank you, Anil. And then we'll go to Miroslav.
Hello, I'm Miroslav Horňák. I'm calling from Brno, from Repromeda, from Czech Republic. I'm in charge of PGT-M program in Repromeda.
Thank you very much. Gary?
Hi guys, I'm Gary Harton. I'm the GM of Reproductive Health at Bioscribe Genomics. Says Durham, North Carolina, where Bioscribe is, but I'm in sunny Florida, as you can see from my face at the moment. So thanks, I'm happy to be here.
Thanks, Gary. Lovely. Celine.
I am Celine Moutou from Strasbourg in France. I'm the head of the PGT Center in Strasbourg.
Lovely, thank you. Joanne?
Hi, I'm Joanne Traeger-Synodinos, or otherwise Joanne. I'm based in Athens, Greece. I am now head of the Laboratory of Medical Genetics in Athens University in the Children's Hospital, IS St. Sophia, and I oversee not only PGD but all the other genetic testing in our lab, but PGD was one of my main focuses and something that I've been doing for a long time.
Thank you very much. And we also have two other authors who unfortunately won't be able to join us live today, and that's Pamela Rennick, who's based at the Guy's Hospital in London in the UK, and Pam has been instrumental both in supporting the EQA over the years, but also running the PGT service from London. And also Martine de Rijk, who again has been involved right from the outset of our external quality assessment schemes for PGT, and she is based in Brussels in Belgium. So as you can see, we've got a fantastic setup today, and we're really pleased, Farah and I, to have the team of our PGT experts here to answer questions for you and also give an update and a summary of where we are with our guidance. Lovely. So Emma, if we can just move through the slides now, please. So I'm just going to start by giving you an idea of what we're going to cover today. We're going to talk a little bit about GenQA and external quality assessment. We're then going to give an overview of what PGT-M actually is and some of the limitations and the benefits of testing. Farah is going to talk about the actual EQA format of PGT itself. We're going to have cover general observations that we've seen throughout the assessment over the 12 years of the EQA. We're also going to talk about disease-specific issues, which has come out of some of the EQA runs, whereby we change the different disorders that we focus on every year, so we can see what is specific to different diseases. Then we'll have a quick summary. So Emma, if we move forward, please. So just a couple of slides just to outline what external quality assessment is. Now, GenQA is the Genomics Quality Assessment Service, and we're part of UK NEQAS. So UK NEQAS is the National External Quality Assessment Services. And the strapline is about helping to ensure that your clinical laboratory test results are accurate, they're reliable and comparable wherever they're produced. Which really means that if a PGT case was tested, for example, in Jan's lab in Greece, that the same result and the same interpretation would be provided than if, for example, it was tested in Miroslav's lab in the Czech Republic. UK EQAS itself is a charity organisation. It's self-funding, non-profit making, which means that we charge a participation fee and that covers the cost of delivering the service. And any excess income is then used to set up new pilot EQAs, and that's what happened 12 years ago to set up the PGT-M EQA. Now, UK EQAS has been around for a long time, over 50 years, providing EQA for a whole range of different laboratory medicine tests, and GenQA focuses on the genomic testing. And despite being called UK EQAS, we're based in the UK, but we have participants worldwide. And in fact, GenQA have about 80% of our participants who are based out with the UK. GenQA and all of the other UK EQAS schemes are also ISO accredited. They're accredited to the international standard 17043, which is for proficiency testing and external quality assessment. So we operate to a high quality service ourselves. So Emma, if we move on to the next slide, please. So GenQA delivers external quality assessment for genomics, and that's the end-to-end path of genomic testing, right from clinical genetic counselling, right through to sample handling, DNA extraction, nucleotide extractions, the actual testing itself for a whole remit of different testing strategies, different methodologies, right through to interpretation and reporting. Now, the World Health Organization defines EQA as a system for objectively checking the laboratory's performance using an external agency or facility. So it's fine for a laboratory or a clinical service to say, we deliver a fantastic service, our standard is really high, you're going to get good, accurate service from us. But it's very different from having an external organization actually endorsing this and proving that that is the standard of your service. So it's very important that laboratories can have the availability of external quality assessment for all the different tests that they perform. So next slide, please. So GenQA has expanded dramatically over the last sort of 5 years, whereby the molecular EQA scheme and the cytogenomics EQA schemes have come together really to harness the change in genomic testing, where now it's about genomics rather than different technologies and different bases. So we've got a global outreach. We've got nearly 1,800 participating laboratories, and we now deliver about 119 different EQAs throughout the year. So next slide, please, Emma. So as I say, it's all about the end-to-end pathway, and here you can just see the range of the different specialities that we cover for GenQA. And I think really it reflects on how genomics has started to infiltrate right across all of laboratory medicine, and really there is a role there to play in many, many different disciplines. But today we're going to focus on pre-implantation genetic testing, and in particular the testing for monogenic disorders. Next slide, please, Emma. This is a very high level format of EQAs, and I thought I would just talk about this to set the scene, because our PGT-M EQAs run in a very nice specialist way, but again is based on the same format of our EQAs. So what we do is we source samples that are as close as possible to the clinical material that's tested by the laboratories, and we validate them quite extensively so we know what the results should be once they're in the hands of the laboratories. We then send the samples out with the clinical cases as a distribution, and then we have online results submission. Then we have a panel of expert advisors, many of whom are on the call today, who have peer ratified marking criteria. These are applied to the EQA reports that have been submitted anonymously, and then the results are collated, and individual EQA provider scheme reports are released, plus individual laboratory reports, such as really giving you tailored feedback to the content of your EQA. And for the PGT-M EQA is more about testing strategy as well going forward for a PGT case. Now, because some of the assessment is about interpretation element of the report, it can be subjective at times. So we have a fully transparent and open appeals process for the laboratories, and then the reports and the scoring is finalised. So that's a quick run through of the end-to-end format of the EQA. So next slide. So as I mentioned, we published a manuscript at the at the end of last year, 2022, summarising the 12 years of assessing the quality of pre-implantation genetic testing for monogenic disorders. And this is what we're now going to talk through this document to you. So next slide, please. I'm now going to hand over to Gary, who's going to give us a bit of background of PGT-M, and then we will move through the document. So Gary, over to you now, please.
Well, thank you very much, Sandy. I really appreciate it. I'm very happy to be here. And I was just thinking as I was getting ready for this, Sandy, that someone once told me that when you start getting invited to do the history of something, you know you're getting to be the old guy in the group, which I think is okay. If you look at the group here, I'm okay being the old guy with this team.
Well, I'll just put it on record that you said that and not me.
Fully transparent, agreed. It's me, not you. So thank you very much. So just a little bit of history. I think if you join this webinar, you're probably pretty aware of how PGT-M works. But in general, let's just cover it to be sure. So PGT-M here offers couples that are at risk of passing on a monogenic condition, so a well-known, easily tracked genetic condition. An alternative to invasive prenatal diagnosis and therapeutic termination of pregnancy, or not having children, et cetera. So it was a sort of a new and extra reproductive choice. It involved the biopsy of cells from an in vitro fertilized oocyte. Originally and early, it was polar bodies. That's very rarely done today, or in vitro embryos, cleavage stage, and or blastocyst, which is mostly what happens today. And I think through the talk today, you'll see the changes in not only genetics and genomics that Sandy alluded to, talking about EQAs, but I think the changes that we've seen in embryology and in the IVF side, from day 3 biopsy, how much ICSI is used to trophectoderm biopsy, and all those sorts of things. There's massive changes, and you can see that through this talk. Next slide, please, Emma. So a typical PGT-M case, this is a diagnostic. This is these people are at risk for something. So this is obviously a broad swipe at what happens across the world, but I think pretty globally, there's some sort of consultation with some sort of medical professional to gather information about the genetic disease. Hopefully we get a pedigree, understand the penetrance, who has it, who doesn't have it, collect genetic reports. We want to make sure that whatever we're diagnosing in these embryos is the problem that the parents are worried about for their offspring. We don't want to go diagnose for something that isn't the actual disease. Then the laboratory then takes all that information and does a pre-PGT workup or PGT workup where they develop a specific test. There are now tests on the market that you can buy that are pan-ethnic and more universal, but still those tests still take some workup to ensure that for this family, the genetics, the way things are inherited through gametogenesis, actually meet up with the expectations of a clinical diagnostic test. So that's done during the pre-PGT cycle. That's typically takes a few weeks to a few months, depending on the test that's being developed and the institutions involved. Once that test is ready and the laboratory is sure that it's working at the single cell to just a few cell level, again through validation, then the IVF cycle starts, followed by blastocyst biopsy, PGT testing, biopsy, freezing of the embryos, and then PGT testing, reporting, counseling, decision making, and then again returning the circle back to meeting with the medical professional to decide what do we do next with these embryos. Next slide, please, Emma. So again, I think through the talk, you'll see great changes in the ways that laboratories not only handle embryos and the beginnings of the diagnostics, but also the way we actually do diagnostics. So early in PGT-M, it was single cell biopsy. So there are questions about whether we take 1 cell or 2 cells, how good a test has to be, or what sort of levels of diagnostic accuracy a test has to have if you're only going to take 1 cell versus 2, depending on the type of disease. This group, a subset of this group, wrote a paper about that. So we would look at short tandem repeats, single nucleotide polymorphisms, almost all by custom designed PCRs with linked markers, hopefully with also direct tests plus linkage approaches looking for the presence or absence of pathogenic variants, contamination, specific amplification issues like allele dropout. You know, misdiagnosis can happen if you have an allele dropout event where one allele amplifies and the other one doesn't. And then we've moved now to more global tests, more universal tests where we can do whole genome amplification ahead of time. Especially multiple displacement amplification, you'll see a lot of that here. Single cells generates high DNA yields with excellent genomic coverage and low ABO rates when you biopsy trophectoderm samples. That's then allowed multiple flavors of testing. One can then do multiple diseases. Patients amazingly come sometimes with a recessive disease and a translocation. And of course, everybody wants to also know about aneuploidy testing on top of that. So the ability now to whole genome amplify with high fidelity a small biopsy from embryo has really opened up a whole new world of genetics and genomics that we're going to be able to be testing. And thank goodness again for the EQA to come behind and make sure that those tests are operated and developed in accurate and you know, excellent lab testing ways. Next slide, please. And with that, I'm going to hand over to Farah and let her take on the more difficult part of how the EQA works.
Thanks, Gary. Appreciate you giving that background information. So the way the PGT-M EQA is set up, it's in 2 stages, and this is to mimic the end-to-end protocols that Gary has just described in the whole process. So stage 1 is a feasibility study, and in this we send out DNA from the parents and an affected proband, and participants, they use a proforma that we supply, and they report the genotyping results. And in this, they outline their testing strategy, and they clearly state any limitations and risk of misdiagnosis, and overall then whether or not they can offer PGT for the case that we are supplying that year. The assessment includes genotyping and interpretation, and the assessors provide feedback on optimal and suboptimal PGT strategies. And then we move on to embryo testing, which is stage 2. Next slide, please. So this is an example of a referral that was sent last year, which was for Duchenne muscular dystrophy. It's a couple that wish to undergo PGT. Their son has DMD and the mother is a carrier. So we will supply the background information and we supply example reports, and then we with the samples, and then we put the case forward for you to test. Next slide, please. So stage 2, once you've finished stage 1, you let us know whether or not you can proceed to stage 2. The way we used to work is then automatically you'd be enrolled to stage 2, and those that couldn't perform PGT, they were automatically withdrawn without any penalty. We used to distribute the samples in 2 separate batches, so stage 1 and then stage 2, but now all samples are distributed together and you've got 10 weeks for testing. So stage 2 is the embryo testing, and lymphoblasts are distributed for mock embryo testing. Clinical participants upload their clinical reports, and then they complete also again another proforma we supply. The haplotype results are submitted, and these are again, the reports are assessed against peer ratified criteria. We're looking at the genotyping, the interpretation, and this time the clerical accuracy also. Next slide, please. So these are the EQAs that we have provided PGT-M for, the disorders that we have provided EQAs for. We started this PGT-M back in 2008, where there were 2 years of pilots, which means that performance criteria isn't applied. And then in the 3rd year, we started applying performance criteria. This year, the case is going to be for Fragile X syndrome. So registration is still open. Next slide, please. The PGT-M manuscript that we are discussing focuses on 8 monogenic disorders that we provided over 12 years, and these are the disorders that are covered. Next slide, please. So this is just to show you the participation. So each column represents 1 laboratory, and a shaded cell denotes participation. So the reason laboratories may not participate every single year is because we rotate the disorders we provide EQA for, so they may not offer that service. So sometimes it's not suitable for them, which is fine. As you can see, in 2008, we had 11 laboratories from 10 countries, and we've moved on. There was a spike in new participants in 2017, and from 2020 then there were 59 laboratories from 25 different countries, and we're much higher now. We're in the 80 laboratories numbers now. Next slide, please. I'll pass it over to Anil now, and who's going to discuss the general observations. Thanks, Anil.
Thank you very much, Farah. Each year we have many important observations regarding the PGT applications of the participant laboratories, and we share these observations in the final scheme report to guide them. GeneQA accept the laboratories to participate EQAs with their own in-house validated PGT protocols or with automated platforms which designs for these applications. And testing methodology shows that these two different applications can be used by the laboratories, and STR linkage analysis was most commonly used despite the widespread adoption of SNP-based more automated platforms from 2013. And almost 60% of the laboratories in 2020 used STR-based strategies for PGT protocols. Among laboratories using SNP-based assays, multiple displacement amplification was the most frequently utilized whole genome amplification method, with, because it's high, very good coverage of the genome, and especially when applied on the blastocyst samples. Laboratories using a SNP approach originally participated using STR analysis and had a period of time whereby they participated in duplicate to ensure EQA of both their SNP and STR testing strategies. In fact, this was a good strategy for these laboratories, where they could compare a new platform, a new method with their already validated strategy. Next slide, please. Since the beginning of EQAs, especially using the single blastomer samples, turned towards the trophectoderm samples, and now today most frequently used samples are trophectoderm biopsy samples. It's more than 77% of the laboratories in the EQAs between 2018 and 2020 preferred to use trophectoderm samples. Minimal modifications to routine practice observed when direct pathogenic variant testing could be performed, for instance, sickle cell anemia, myotonic dystrophy, or cystic fibrosis. When the supplied samples did not permit direct testing, such as Huntington disease, spinal muscular atrophy, or BRCA EQAs, an impact on testing strategies employed by participating laboratories was observed. Testing often relied on the use of markers further away from the disease-causing region to achieve a minimum number of informative markers to compensate for lack of direct pathogenic variant testing. Next slide, please. Some laboratories only use published markers that were often quite distant from the gene of interest and therefore not relevant to the PGT-M case. This was particularly apparent in BRCA EQA, where numerous STR markers, including intragenic ones, were available for linkage analysis. Also in the MD EQA, which resulted in large regions of the gene not being covered, precluding accurate assessment of recombinant haplotypes. In fact, this observation shows the importance of the flexibility of STR-based protocol, where the laboratories can improve the robustness of their protocol, adding new STR markers within or near distance of the gene of interest. And assuming homozygosity was another observation we had, in every EQA, it was observed that many laboratories assumed homozygosity of allele genotypes in the embryo samples, which potentially overlooked the occurrence of ADO. In fact, during the stage 1 analysis, this can be considered when you are working on the extracted genomic DNA samples, but on embryos, allelic dropout is a big issue even in the few cells. So this observation is important to consider the embryo samples not homozygote, but considering the allelic dropout occurrence, potential allelic dropout. Next, please.
Thanks, Anil. We're going to Celine now. Celine?
Yes, thank you very much for letting me talk about this very nice project we have since many, many years. So I will talk about a few specific issues we had during these different EQA schemes. And I will start with the Fragile X syndrome scheme that was done between 2011 and 2012. So for the stage 1, there were 25 laboratories that was registered, and 24 of them could offer PGT after stage 1. And at this time, all the labs were using STRs, either alone, that was for 6, or in combination with the mutation detection. So for Fragile X syndrome, it's special because the expansions cannot be detected. So the direct CGG repeat only considered the normal repetition. One laboratory did not offer PGT and did not move to stage 2 because of the lack of informative markers in his own strategy. For stage 2, 2 participants were not assessed as their strategy proposed in stage 1 was not appropriate for stage 2. Recommendations were done on the final report for this EQA, 2 major ones. One is a general one, and the second one is specific for Fraxas PGT. So in general, for PGT for X-linked disorders, the strategies should include sex determination by testing the presence of Y chromosome using different markers, a sufficient number of genetic markers. And specifically for Fragile X syndrome, centers using the FRAX-AC2 marker should be aware that this is a 1 base pair repeat marker, so the results may be difficult to interpret. Next slide, please. There were 2 EQAs for Huntington's disease, which is also a repeat disease. Thank you. The first one was in the early years of EQA for PGT. It was in 2012 and 13. And a few years later, in 2019, we had a next EQA. So in 2012, all 27 laboratories performed STR-based linkage analysis and using 36 different STRs. In 2019, there were 56 participants. 2/3 of them used the STR-based analysis, and 1/3 had introduced the use of SNP analysis. And finally, 3 other laboratories were not able to offer PGT for the couple that was included in this EQA. On 2012, stage 2 included a trap. Yes, there was a mock embryo that had only maternal contribution. And finally, it was correctly detected by all the participants, which is a very good point. For Huntington's disease, 3 recommendations emerged from this EQA. The first one is to use markers within close proximity of CAG repeat in order to have a good and robust strategy. There was a warning about one marker, D4S126, which location to the gene differs according to the genome reference used between HA18 and HA19 builds. And finally, a terminology recommendation, since some participants use the term affected and carrier when we deal with exclusion testing, which is not recommended. It is recommended to use the test at risk, the terms at risk or not at risk for the embryo status when we're talking about exclusion PGT. Next slide, please. Another repeat disease is a myotonic dystrophy type 1 for the DM1 gene. So this EQA was run in 2014-15. And there were also 25 laboratories who participated in this EQA. 20 used STR linkage analysis, and 3 used both STR and SNP analysis. 1 participant could not offer PGT, so could not go to stage 2 because the laboratory said that they need more than one meiosis to do the linkage analysis. And they participated on stage 2 just for educational purpose, which was also a possibility. And another one did not participate in stage 2 because of a lack of informative markers in their laboratory. As trophectoderm biopsy was increasing at this time in the PGT community, for the first time, EQA offered the participant to choose the number of cells to be tested. So either single cells to mimic cleavage stage embryos, but also multiple cell samples to mimic blastocyst stage biopsy, or some laboratories asked both to test both strategy. For stage 2, 3 mock embryos had to be tested, 2 affected, and 1 with a maternal contribution only. And 2 laboratories failed this time to detect this maternal contribution only. And finally, it was noticed that half of the 66 STRs used were too far from the CTG repeat. 25 were more than 1 megabase and 10 more over 2 megabase, which is not recommended by the classical recommendation for PGT. And this is even more important when you have closer markers. Next slide, please.
Celine, thank you very much. So Celine just took us through the repeat expansion disorders that have been included in schemes for the PGT EQAs. And I'm going to talk about the recessive monogenic diseases that we've had schemes for so far. So the first one was for sickle cell anemia that was in 2003 to 2014. This was the first time that laboratories used SNP analysis and specifically carrier mapping in this particular at this particular time. And of note was that one laboratory incorrectly reported a homozygous result instead of a heterozygous result. So this was a mistake that they were marked down for. So based on the results from the scheme, in which there were, I think, about 29 labs taking part, 3 laboratories used PCR-based whole genome amplification, specifically the Shortplex method, which is actually not recommended when doing STR analysis. And therefore, this was something that was noted on the reports that they received back. Because multiple displacement amplification is the preferable method for doing PGT-M. And also specifically for this scheme, there was one marker within the beta-globin gene cluster that was observed to have extreme variability in allele sizes, and it was recommended following the scheme that this marker should be avoided in future applications. Emma, could I have the next slide, please? So with respect to CF, which was in fact the disease that was selected initially as the pilot disease for the first few schemes that were run, presumably it's also because it's one of the most common, if not the most common in many populations, autosomal monogenic disorder. And by 2017, the number of labs had gone up considerably. We're talking about 47 labs that submitted 52 sets of results because some labs tested single cells only and other labs tested 6 cells as well in stage 2. 35 labs performed STR analysis and 15 used SNP haplotype analysis, indicating that the use of SNP haplotype analysis is on the increase since the previous slide that I showed you when this method was just used for the first time in 2012-13. Now, issues that were noted following the marking of this scheme is that not all of the 15 labs that use SNP haplotype analysis submitted a feasibility study in stage 1, and this is strongly recommended before applying a clinical SNP-based PGT-M cycle, so that we're sure that there's sufficient informative SNPs available to give a robust result when testing the embryo samples. And if there's not, then it's probably best to use supplementary methods, for example, in stage 2 with STRs or direct variant detection, if this is possible. With respect to 3 laboratories that performed carrier mapping, there was minimal informative SNPs for the 3' region of the CFTR gene. In fact, just 3 labs of the 15 did use supplementary methods for this reason. Could I have the next slide, please? So the most recent recessive monogenic disease that we've applied for a PGT scheme was spinal muscular atrophy. We had, I think, a pretty much record number of labs. I think it's about 59 labs that were included in this scheme. A number of the STR testing laboratories described poor testing strategies. In stage 1, they didn't have sufficient informative markers for distinguishing the low-risk parental alleles, especially for the region that is centromeric to the SMN1 gene. And therefore, due to these limitations, 8 laboratories did not go on to perform stage 2. 17 labs were perceived to have a weak strategy, and 3 a very weak strategy. They didn't have enough informative markers, especially for the identification of the low-risk parental alleles, which is extremely important when we're doing preimplantation genetic testing for monogenic disease. It's really the presence of the unaffected alleles that we're looking for rather than the affected alleles in order for us to be sure that we haven't got a misdiagnosis. There were few informative SNPs with respect to the SNP arrays around the 2 megabase region centromeric to the SMN1 gene for the parental low and high risk haplotypes. And although in some cases it's acceptable to exceed a distance of 2 megabases, which is what is usually recommended, there's an increased risk, of course, of missing a double crossover. And overall, 4 laboratories with a SNP-based protocol selected not to continue to stage 2. Now, could I have the next slide, please, Emma? This scheme actually was quite a difficult one because the fact that we were using mock cells meant that we couldn't allow the labs to do direct testing for the SMN1 gene deletion. And the fact that the family was not informative for many markers as well was a drawback for this particular scheme. And this was compounded also by the fact that there's high sequence homology for the region around the SMN1 gene. And so many laboratories decided to include additional markers that were further away from the SMN1 gene than usually recommended. Some laboratories also included multi-allelic markers in their STR protocols, and this was because within the region you've got homologous sequences in the locus, and therefore these markers should be used with caution because they can be quite ambiguous to interpret. 8 of the SNP testing laboratories, which is 1/3 of all of the SNP testing laboratories, did not demonstrate awareness of the risk of a double recombination event and in their interpretation, and therefore deductions were made for these laboratories. So with that, I think I finished the recessive monogenic diseases, and it's over to Miroslav.
Yes, thank you very much, and I would like to continue with the specific issues for EQA scheme in 2018, which was focused on BRCA1 gene. As we can see, there was high attendance and 44 labs returned results, and the STR markers prevailed over SNP markers, but we could see these years that especially carrier mapping and other genome-wide arrays were slightly increasing in the numbers. Another strong trend we observed was shift from testing of blastomeres, so day 3 samples, to day 5 samples to trophectoderm samples of the blastocysts, which was very compatible with the freeze all strategy. So all blastocysts were sampled, frozen, and it was lots of time for the analysis. As a preferential method, WGA MDA multiple displacement was used, which is very good, very nicely working on multicellular template, so on trophectoderm samples, allowing downstream applications like STR analysis, SNP analysis, or even NGS. Next slide, please, Emma. There were some specific issues to note. For example, one laboratory was given a critical error in stage 1 for an inappropriate testing strategy used. Some laboratories offered kind of tailored testing strategies using, for example, combinations of SNP and STR markers to improve informativity of the tests. One laboratory included the sexing of the embryos in this particular BRCA scheme, which is kind of opposed to the most prenatal testing strategies, where it's not recommended. However, in that case, it's understandable because we know that lifetime risk for cancer is really different in male and female carriers. So probably there was some kind of extra information needed for genetic counseling in this scheme. Some laboratories enlarged the flanking regions up to 3 or even 5 megabases, however, without providing clear explanation why they did this. And also it should be stated in the limitations when these regions are enlarged, it means automatically there is a higher risk of recombination, and this should be the laboratories should be aware of this. So next slide, please, Emma. Another scheme in 2016 was focused on Duchenne muscular dystrophy for DMD gene. Again, we have many laboratories which participated. 42 could offer testing and were able to perform the whole scheme. 2 labs did not have either informative primers, or there were some technical issues, so they did not continue. Some laboratories wanted to test both templates, so single cells or multicellular cells, so trophectoderm cells. So they wanted to have both cells to be sent to them, and also they wanted, for example, to test STR or SNP array analysis, so they also used both protocols for testing. There was a particular issue in this scheme, and it was a very or more than average number of failed samples which were sent by us to the laboratories. And we were discussing the conditions of transport and possibly the oil which was used to overlay the cells in the tubes. Fortunately, majority of the labs have no issues, and in the next years it was okay, so it was solved. And also there was a very specific recommendation for this particular scheme, because we were testing DMD gene, which is really large. It's spanning 2.4 megabases in the length, and it comprises more than, actually it's 79 exons. So the laboratories should be really aware of physical distance of the markers they are using to the particular mutation, because as the gene is very big, the distance can differ dramatically. So in these large genes, it's recommended to use intragenic markers, which are spread in the introns or even exons of the whole gene to achieve optimal coverage, optimal marker coverage. And especially this is a topic because DMD is also a recombination hotspot, so there can be increased risk for the recombination. So really numerous markers should be used, and intragenic preferred. So thank you, and I will hand over to Sandy again.
Great, thank you, Miroslav, and all of you. So really, to summarise, I think we can demonstrate and show the evidence that the PGT monogenic disorder testing field has changed really quite significantly over the last 12 years. And this is, I think, the power of having continued annual participation in such a scheme as EQA, that you can actually see how testing and the strategies evolve going forward. From GenQA point of view, that's challenging because we have to keep up to date and make sure that our EQA schemes are fit for purpose for what's happening in the real world, whether that's methodology changing, platforms, testing strategy. So we need to make sure that we're not biased in any way, to make sure it's an agnostic approach so anyone can participate in the assessment, and you can get the benefit from that. We've demonstrated that providing the labs with a two-stage distribution, and it's quite unique, this EQA, to be able to do that. We're covering both the feasibility or the sample workup element and the embryo sample genotyping using different sample types, the format of marking reports and the feedback that we're giving, and really a lot of that is based on not just the EQA staff but also our expert advisors on that true scientific knowledge and expertise that's brought to the assessment. I think really we have a good and robust EQA. And also I think it's been really important over the years that we do change the different diseases that we focus on, and because some labs don't test for all of the scope of potential monogenic disorders, so we can maximise the amount of laboratories that are able to access the EQA depending on which diseases they test for. So next slide please, Emma. So I would say, I think the quality of PGT-M testing across the world, global, because these laboratories are from all parts of the world, is really very high. We only see a handful of labs receiving scores for either stage 1 or 2 that really require a lot of feedback and follow-up and support from the expert team and the EQA provider. We do see deductions for small omissions or maybe not quite robust testing strategies that we'd be looking for, but I think overall the performance is very high. So I think it implies that the majority of patients who do undergo PGT-M globally are getting really good tests and high quality, and that the reporting, not just the testing, but the reporting is safe as well going forward. So I think that is definitely good news. So next slide please, Emma. So I'm really pleased to see we've got questions coming in, so please do add your questions into the box and we'll work our way through them. And I'm now going to open the session up to all of our everyone on the call here, our panel, and I'm going to kick off with Farah. A very easy one for you actually. There's people saying, how do you register if you've never participated before, and what's the disease for this year 2023 and for 2024?
Okay, so for this year, the disorder is for Fragile X syndrome. And if you're, please go to genqa.org, the website, www.genqa.org, and you can register by joining us. If you have any queries, please feel free to contact us. On the slide below, there's an email address, info@genqa.org, and we'll get back to you and provide any support you need to register. And for next year, we're looking to source samples for beta thalassemia. So these are the EQAs that we have got planned at the moment.
Great, thank you, Farah, very much. I've got one here about Y chromosome markers. Celine, I think you mentioned that when you were talking about one of the triplet repeats, like cracks. So how many Y chromosome markers should I use for sex determination?
So there is nothing in the ASHRAE recommendation for the numbers of Y chromosomes that should be included. So it's difficult to, as an AQA, to force people to have 1 or 2 or 3. But during our discussions, it was clear that there should be at least 2 Y chromosomes, if possible, in the strategy. Y chromosome markers, sorry.
Yep, That's great. Thank you very much. That's helpful. Jan, you've been assessing for quite a few of our EQA runs now. So we see different approaches of how the embryo results are reported. So somebody's asking, should multiple embryo results be put on one report, or is it better to have individual reports per embryo? And I know that's something that we observe when we're doing the assessing.
Yes, I think, again, there's nothing in the best practice recommendations for such a strategy. I think it really depends on the practices that are local. But generally, because the embryos are generally batched per couple, I personally find it easier to evaluate the results if they're all in one sheet as a table. But I mean, I think it really depends on what practices one is used to more than anything else.
Yeah, I think if I might here, Sandy, I think, yeah, this is Gary. So I think one of the things that Jan brought up is, which is quite interesting, having been involved from the early days, and is local and regional differences in even the way we report things. Words that we use in an American report would never be used elsewhere in the world, and vice versa. And it created, early on, it created some strife between groups going, well, this is how we report, right? So the EQA says, report this the way you would ordinarily report it, but then that doesn't meet the criteria. So I think one of the other things that came out of the EQA that Jan mentioned here was sort of just local differences in the way reports are written and the way information is communicated, which is, for me, quite interesting to see how that changes, and how that changes the way reports look and feel, and the what they can communicate to the patient.
Yeah, absolutely.
May I add something?
Of course.
Yes, I think there is also a difference between people who have different IT systems, because some IT systems report sample per sample, and maybe that's why we have some labs who report per sample and other labs who have a global report.
Yeah, and I think that it just demonstrates that, as I was saying, we have to be quite agnostic to approaches and testing strategies and reporting, because we need to make sure that we can assess all different ways in the lab. There's not always a one size fits all that's the best way forward. So we do have to be adaptable, don't we, to how we apply the marking. Yeah, thank you. So we have a question here. I think maybe Miroslav, you want to take this one? What is the stance on coupling PGT-M and PGT-A, since carrier mapping allows also to screen for chromosome aneuploidies? Oh, I think you may still be on mute.
Okay, thank you. Yes, I realized. So the question was about combining PGT-A and PGT-M, I guess. All right. So yes, I think that's about the policy of the IVF center, which way they prefer. Of course, now there are many strategies, genome-wide SNP arrays, NGS strategies, which can do simultaneously both. So of course, it's beneficial and advantageous to see some meiotic trisomies, for example, to prevent transfer of pathogenic variant free embryos, but with some kind of aneuploidy. So if the technology is capable of doing aneuploidies, and it's counseled with the patients, the technology can be used with some kind of advances over traditional only focusing on the pathogenic variant.
Yeah, thank you for that. We've now got a very specific question. So for X-linked disease, what's your view on performing only the pathogenic variant testing, such as SNV detection in G6PD gene by sequencing in male embryos, provided that MDTA was used and no allele dropout was observed? Who would like to take that one? Do you want me to repeat that? So basically, by doing a sequence on a male embryo for a pathogenic variant, a known pathogenic variant, if you're using MDA and there's no allele dropout.
Can I just ask how you would prove there's no allele dropout if you don't do any other markers?
I think
Just
that
by
would be the concern, I think.
just by
Yeah.
the same sequencing. Yes, personally, I wouldn't recommend not using linked markers.
I mean, I think all the recommendations say that you should do a direct test and linked markers if you can. I think that's recommendation stays.
And if you MDA your cells, you have plenty of DNA to do many things with it.
I don't know why one would select to do such a simple test for such a highly demanding application, such as PGT, when you're dealing with such a small initial sample. I personally wouldn't recommend it. I don't know about anybody else.
No, I think we're all in agreement there. Lovely, thank you. So I'm very aware that we're at the top of the hour. We've had loads of questions. I'm going to just end on one more, which is about carrier mapping. So question, how many SNPs are necessary to discover phasing? So maybe Miroslav, I'll come to you because I know that you do carrier mapping in your own laboratory.
There are some extra recommendations, so it should be at least 6 SNP markers so upstream and downstream of the gene. But of course, for carrier mapping, usually there is no problem to achieve much more informative markers. So if there is no some specific issue like consanguinity, it should be not be problem to see dozens, 30, 40 informative SNPs at the 2 megabase region around the gene. So definitely the 6 is the minimum to be safe on both sides, to exclude or to prevent risk of double crossing over. And then hopefully there will be much more.
Brilliant, thank you. So worst case scenario 6, but hopefully there'll be better coverage across the genome, the area of interest. Lovely, thank you. Okay, so if we move on please, Emma. And the next focus on topic will be the sample handling EQA's feedback, which will be towards the end of May. So we hope you can join us there. Thank you very much, everyone, for joining us today, and a massive thank you to the expert panel for taking the time from multiple different countries across the globe to join us today on the live webinar. So thank you very much. I hope you've found it useful. Thank you.
Thank you very much, Sandy, for organising this, and Farah as well, and to everybody else on the special advisory group that we've been working together for such a long time.
Brilliant. Thank you all.
Thank you all. Bye-bye.
Bye.
Bye.